When you apply amyloid beta to a culture of these astrocytes, you start to see an uptick in the activity, in the calcium activity of these astrocytes. And so you'll see these cells start to all of a sudden oscillate. So the calcium increases and comes back down. And that starts happening more and more after you apply the amyloid beta. What you also see now is these coherent waves where one cell is going to have a transient elevation, and then that elevation is going to spread throughout a whole network of cells. And so you might have now 50 cells or 100 cells involved in the same wave. This only happens after we apply the amyloid beta. So what you're looking at here is simulating a culture of these cells now with the equations and running that and to see what happens in our simulation when we apply amyloid beta. And what you'll see is from the beginning of the movie is not much activity right after we apply the amyloid beta. And then eventually you'll see some cells turn red, and the simulation turning red is equivalent to a rise in calcium. You'll also see white coming out from the cells, and that is the spread of chemical messengers between those cells as we track it. Just to the left of the center, you'll see a wave nucleate after about 20 seconds of the movie, which is 240 seconds in the real time. The wave nucleates and forms and then spreads throughout the culture, much like what we see in the amyloid beta experimentally. I look at the mechanistic interpretations of the data through mathematical modeling. We see what is happening, but the question is why. And to do that, we need to probe a little bit deeper. Why does amyloid beta cause these waves, right? We know it does, but why?
And that's what you said future papers, future experiments, that's what you're working on now, is that right?
Yes, that's correct.